Hi, I'm Todd Austin. This is part 5 of my 6-part hardware security tutorial video series. And in part 5, we'll be talking about software and hardware security defenses. Specifically, in this part, we're going to look at defenses in software and in hardware that are protecting our systems today. And we'll see what approach they use, what attacks they can stop or detect, and then we'll look at some of their shortcomings as well. And then in the final part of the series, part 6, we'll take a look at emerging defenses. So up until this part 5, we've set the stage why security and hardware security is important. We looked at the basics of security. We looked at hacking and side channels. And so now we're going to look at some existing defenses, hardware and software defenses. To the hardware security architect, sometimes defenses are best in software, sometimes they're best in hardware. We'll see the trade-offs there today as well. And then in the last part, we'll look at emerging defenses, which will include a lot of my research and other research, things that are in the field today, but things that are developing and coming down the pipe. All right, let's get started. First thing I want to talk about is safe languages. A lot of security people roll their eyes at vulnerabilities and say, hey, why aren't you programming in a safe language? What is a safe language? A safe language are languages like Rust or Python or Java, which don't allow memory access errors, which many vulnerabilities are based on memory access errors. So what's a memory access error? A memory access error is basically a program accessing an array variable in a way where it can go past the end of that array. So, for example, here we have access to an array that has 100 elements, but we index it with 101. And so we're accessing memory that's actually outside of the array. In a language like C or C++, you can do that. It doesn't try to stop you from going past the end of an array. Array boundaries are just advisory. They're not actually enforced in the language. That's called a spatial memory access error because you've gone outside the space of the variable. You can also have a temporal memory access error where we allocate some variable under P1, we copy the pointer to P2, we free P1 and we give it back to the heap. It's a dynamically allocated variable. And now somebody still holding P1 accesses the variable that could be allocated to some other variable now. And so you're outside of the temporal bounds of the variable. You've been able to access it. Again, languages like C and C++ don't try to stop this. Now, safe languages, let's take Java, for instance. Java does check, are you going outside of the bounds of this array? It knows how big an array is and it enforces those bounds. It also enforces the temporal aspects of it by not releasing storage until no one points to it. And that's done with what's called garbage collection. And so typically what you'll see is array bounds checks to stop spatial errors. You'll see some form of either reference counting or garbage collected storage management where there's no freeing of storage. When you're not using it anymore, the system is aware of that in these safe languages. So are safe languages safer? And I always like to show, go to these lists of top vulnerabilities on the internet. And this was from a list that was published in 2020. And they showed like of the top 5 vulnerabilities, one is a Java VM attack, another is a JavaScript deserializer attack. The next 2 are also serializer, deserializers, and XML parsers for Microsoft ASP.NET, which is associated with C#, which is also a safe language, and then Perl, which is also a safe language, an attack on it. And these are all high, very high vulnerability, very serious events. So why if safe languages are so safe, then why is it they're all being attacked? And well, it's because they're very popular and they're everywhere. So you got the population issue. You've got so many instances of these languages everywhere. JavaScript is running in every browser. And so, of course, attackers are going to find ways to attack them. So safe languages are safer, but they're not a panacea, right? When they're very popular, people will find ways to attack them. And typically what they'll do is, instead of attacking the language itself, they'll attack the runtime of the language. And for many of these systems, their runtime is programmed in C and C++. So it's easy to get access to code in the execution environment that was compiled without these safety checks. Now, Rust is particularly nice, right? Because Rust compiles all the way down to the assembly. So there is no part of the Rust system that's implemented in C or C++, which makes it, a particularly nice, safe language. But, it's likely you can still violate Rust checks as well using a variety of techniques. Right now, it's mid-2023. I'm teaching an advanced computer architecture class, and I've got some students working on a project to basically use Spectre and Meltdown, which we learned about in the last lecture. That's a way to do code injection on the misspeculation path of a microprocessor. They're basically using that to try and violate array bounds checks inside Rust. And if I were a betting person, I would definitely bet that they're going to be successful at that. So, safer languages are safer, but they're certainly not a panacea. But if given the choice, if the safe language can meet your performance and goals, then why not use a safe language? You're certainly going to reduce your attack surface with all the additional temporal and memory access error checks. And it's likely going to be more productive too, because the reason why these languages are so popular is because it's very efficient to program in these languages. They have lots of high-level capabilities. So while we know that safe languages are not a panacea, we certainly, in my world, we certainly like safe languages and advocate for them. All right, let's look at some, very simple hardware mechanisms. This mechanism is available everywhere, and it's basically the no execute bit on page table entries, which allows you to restrict where code can be executed and where code cannot be executed. So, for example, we talked about in a previous episode, where, we're not going to allow any code execution on the stack, and most systems today do not permit code execution on the stack. The way we implement that is by using the no execute bit on pages that are allocated for the stack for a particular process. And in fact, in the heap, we're not going to allow any execution unless it's a JIT page. And in that case, we're going to allow only execution on those pages. And we're not going to mix data and code, hopefully, in those pages, so that we know which pages are executable and which pages are not. And, most modern architectures support this capability. And what it does, it means that it's more difficult to do code injection because there's less places where you can actually execute code. It's just, on these pages, if anyone tries to fetch an instruction from these pages, we'll see in the page table entry that it's not executable, and we'll have an exception the minute that instruction gets into the front end of the microarchitecture. Another great defense, which is pervasive, it's everywhere. It's in your servers, it's on your phone, it's probably in many of your IoT devices as well if they do any code loading, is address space layout randomization, called ASLR. Okay. And the goal here is to basically randomize where information in a program is loaded into memory every time you load the program into memory. So every time you run your program, every time you reboot your system, every time a request is made that initiates this program, the program gets a random orientation in memory. And the way we do that is by adding padding at the start of these various sections. We've got padding before the global variables, we've got padding before the heap location, and we've got padding on where the stack starts in memory. Now, on a 64-bit address space, there's lots of room to make these paddings very large and very random. And so it's it's like looking for a needle in a haystack, a universe-sized haystack to find where's the stack, where's the heap, where are my global variables. Interestingly, many of these systems do not move the code. The code's always in the same place. And this is just because lots of architectures don't do PC relative addressing and jumps very effectively. 32-bit x86 didn't even have that capability, got introduced with 64-bit x86. So still today, a lot of systems are not moving the code. So the code, where the code is located. When this ASLR is fully engaged, it's really hard to do. For example, remember the prime plus probe attack, where you have one process snooping on what another process is doing by looking at their contention in the cache. With this random padding, I don't know where your functions are in the cache. I don't know where your data is in the cache. I don't know where your AES key tables are because I don't know where your static variables are located. I don't know where your heap is. So in order to implement this, you need to have either a pointer disclosure. So somehow a pointer leaks out of the system. And that can be just as easy as like a debug message. Often debug messages will leak pointers and give people enough information to attack the system. And it's interesting, you may not necessarily leak the pointer you want, but if you leak a pointer and the distance, this is called a relative address attack, the distance to the thing you want, then you need any pointer from that section, right? Let's say you're doing a heap spray attack. If I can leak one pointer from the heap, then I know roughly where the heap is. Now I can do a heap spray attack. So disclosures of pointers are a bad thing. If you remember back to the heartbleed attack was a disclosure attack. And what it did is it revealed where stuff was in memory, and it revealed pointer values. And so that was particularly dangerous because now once you have disclosures, your ASLR is not very effective. There's also some really interesting attacks. One that I'll mention is the ANSI attack, with AN capital C, which is an attack which basically looks at how the caches handle TLB misses, which are, they have to walk the page tables, and they look at how these TLB misses walk the page tables by looking at how the cache is being accessed during these page table walks, and they can essentially reverse engineer 64-bit ASLR. Really interesting attack. So clever. So I would say today ASLR is certainly a popular defense mechanism, but for anybody that's very dedicated to get around it, it's certainly possible to do that. Certainly possible. So ASLR, that's a software mechanism supported by hardware because we have flexible virtual memory systems. Here's it's just a simple software mechanism that's gotten a lot of adoption in the last few years. I think most Linux platforms are running this, and it's called Stack Canaries. It's very simple little optimization. The basic idea, if you remember that buffer overflow attack, the way we're going to do a buffer overflow is we're going to overwrite local variables, and then we're going to go past the end of the local variables, and then eventually we're going to get to the return address. Now, what the stack canary does is it puts a random number, which is selected when the program starts execution. So every time you run the program, this number is different. And that's called the canary. We put that canary number between the local variables and the return address. And so if you're overwriting with, like a mem copy or any kind of going off the end of the array thing, typically you're going to have to write all the way through the stack frame up to and including the return address, which means you're going to have to overwrite the canary. And so you need to know what the canary value is. And so the canary value gets set when you call a function. And when it returns, it checks to see if it is the correct value. The way it does that is somewhere in the global section, there's the canary for this instance of the program, and it compares the two. And if they're not the same, then, someone overwrote my canary. I'm going to terminate the program. It's pretty inexpensive. It's pretty effective. And it makes, the simple buffer overflow attack very difficult to do because you got to be able to guess what the canary is. I'll tell you two ways to get around the canary, both super clever. One way to get around the canary is that heartbleed attack. Just bleed out memory. If you can see memory, you can find the canaries. And once you know the canary, you can do it. My favorite technique for getting around the canary is it was this attack that came out of Berkeley called BROP, blind ROP. And it's a blind hacking technique. So it just basically instruments and analyzes the system. And in this particular attack, they were attacking a web server. And then every time the web server got a request, it would fork off a version of itself. And the problem with that is when it forked off a version of itself, it had the same canary as the base system. It didn't change the canary. Mistake. When you don't change the canary, then what they would do is they would come in and they would just overwrite the first byte of the canary. They would write a 0, then they would write a 1, and they would wait until the server didn't crash. And it's only 256 things they have to try. Eventually, it doesn't crash. Now we know the first byte of the canary. Now I write that byte, and then I write the second byte of the canary, and I wait to see if it crashes. So, key point here is if your canary doesn't change every time you fork or exec a new process, you've certainly given your attacker the ability to reverse engineer those canaries. But in general, this is a pretty inexpensive, pretty effective technique. Most versions of GCC are running this today. Here's a sort of a more heavyweight, little more interesting approach where I'm gonna protect the pointers in the system directly. This is called point guard. This is a software-based technique, but in the next lecture, we'll see a hardware-based technique that I implemented called Morpheus, which does the same thing. And the idea is when you look at a lot of different attacks, where the pointers come from is outside world, right? Remember that buffer overflow attack. We're overwriting, and then we're overwriting the return address. What are we overwriting that with? We're overwriting that with a pointer that's coming from the outside world. Now, the attacker has studied the binary. It knows where stuff is located. It knows where the stack frame is located. So it knows to jump into the stack frame, and it knows how to manufacture an address. If there's ASLR in the system, they have to leak out a pointer, then they can do that as well. But the pointer comes from the outside world. So the idea here is let's just encrypt our pointers for the whole program. Code pointers, that's pointers that jump to code. Data pointers, pointers that access data. With a key that's instantiated and unique to every execution of a program. Every time I load, fork, exec a program, I have a new pointer that encrypts those pointers. Now, this is a software-based technique. The pointers are encrypted with XORing with a key. Let me just say, XORing with a key is the absolute weakest form of cryptography. It's super easy to break. We'll talk about that in a bit. And so every time you load a pointer, you have to XOR it with a key, and then you get the real pointer, and then the CPU uses that. Now, if somebody doesn't know what that key is, they essentially have created a random pointer. Because, if I inject the pointer what I think it is, and then you XOR it with the key, which is a random value, I'm going to get a random value out. And I'm probably going to get an exception. I'm going to access a part of the address space that isn't in use. And so I really need to make that guess in the first try. Otherwise, I'm dropping core dumps all over the server. And, a clever IT staff member is going to figure out somebody's attacking this system. It's a little more expensive because every time I use a pointer, I got to do this decryption op, which is just an XOR, but it is more instructions. I can apply it to addresses and function pointers, so I can stop code injection. I can protect my return addresses with this. Really fantastic technique. Pretty easy to defeat, though, because XOR encryption is so weak. Let me give you an example. Let's say I know a pointer in the system, and I can get the system to leak that pointer through a disclosure like Heartbleed. Well, if I know what that pointer is, I just XOR the value it should be with what it is, and then the result of that XOR is the key. So super easy. And if I just have a way to disclose memory, read memory out with Spectre or Meltdown, for example, I can just read the location that has the key in it because the key is just sitting in memory with all the other data. So pretty easy to thwart, but definitely, yet another barrier to manipulate this. I'll also say another thing that's great about pointer protections is it's hard to find a security attack that doesn't need to forge pointers, Pretty much every one of them do. Even advanced attacks that people worship, like data-oriented program. We're not going to cover that, but it's, people go, oh, this is so amazing. You're not even injecting code. You're repurposing my interpreter. Still got to manipulate pointers. So it's hard to find an attack where you don't have to forge pointers, and systems that make forging pointers difficult are really powerful. And we'll look at some other techniques to make forging pointers difficult. So it's just a really great way to like throw a wrench into thousands of different vulnerabilities at the same time. All right. We looked at ROP 2 lectures ago, and we love ROP because it's the ability to reuse code in a way that is not a lot, that the programmers didn't anticipate. And then here is a technology that can stop or make ROP very, very difficult. Now, the reason why ROP exists is, when I return from a function, I can return to any address in the address space. And so the way we do ROP is we pick, tails of functions to stitch together, and I build a return address, and I just jump to those instructions. FYI, 99% of those targets are not legal targets in the program. I'm jumping into the middle of basic blocks. I may be even jumping into the middle of an instruction to create a new instruction. That's a pretty popular technique. When you don't have the instruction you want, you look for it embedded in another instruction. So the ability of a return instruction to jump to any other instruction, the ability of an indirect call, a call through a register to jump to any instruction, allows attackers to really create any code they want to run. And so what control flow integrity does is, instead of allowing, returns and calls through a register to go to any instruction in the program, it only allows certain targets to be made. And those targets are entry points of basic blocks and entry points of functions. And all the remaining addresses are these red addresses, and they're violations. If you attempt to jump to those locations, you will create an exception. And a great example of this is Intel's Microsoft CFI technology. Microsoft really piloted this technology, and they did a software-based version of it. And then Intel has been previewing something called Intel CET, which is essentially a hardware-based version of this technology, which is now available. And it's a pretty good technology, simply because it makes arbitrary jumping through the code no longer possible. You have to go to locations where functions return, and that makes it significantly reduces the flexibility you have on generating ROP. Now, of course, there's attacks that have shown that, like, skipping a return and going 2 up the stack, can create vulnerabilities that are very interesting. That is true. This is not a panacea, but it certainly makes it way more difficult to do any form of ROP on a system. If you've got a choice between a system with CFI on it and a system without CFI on it, I mean, if ROP is one of your approaches, you're going to definitely go for that system without CFI. These are very, very limiting environments for return-oriented program. They're limiting because, they really restrict where you can go. But of course, the control flow graph of a program is not precise, right? There's indirect jumps in the program, and the indirect jumps can go to many different places. And sometimes we don't know all the places it could go to. It could go to any basic block. And sometimes it's imprecise, and we have to allow, places where you can jump pretty much anywhere. Really great technology, really inexpensive, really powerful, and really makes code injection really hard to do. Glad to see this tech is becoming more and more popular. Something that's particularly popular in browsers, where you essentially have a process context for every tab in the browser. And within the tabs of the browser, we're running JavaScript, we're running WebAssembly, where you can just literally download code into the browser tab. We want to make sure that the browser tabs don't interact with each other in any way that isn't allowed by the browser. And we want to make sure the browser code that's running within that process doesn't break out and do things with the operating system that we wouldn't approve of. And so what has become very popular in the browser world for these tabs is something called sandboxing, which is, I love the approach. The approach is basically assume every tab is dangerous, and so limit its power to affect the system such that you don't have to trust it. It's really a zero trust approach for code running on the machine. And so a great one to look is a native client sandbox on Chrome, which is very effective at protecting you against any kind of nefarious code that's inside a browser tab. Essentially what it does is it allows the code to run inside the sandbox, which is associated with the tab of the browser. But the code is not allowed to make any system calls directly. It has to go through the sandbox architect, the broker, and then the broker has policies for these tabs and says, are the things they're trying to do okay? If it is, I will make these calls for you on behalf of you to the operating system, let you access your HTML5 permanent storage, etc., for your storage, not someone else's. And so they run in a very restrictive fashion. Now, one of the things you have to do, you have to prevent arbitrary code execution within these native client sandboxes. And so Google has this fantastic technology called the native client NACL execution format, which essentially makes pretty close to impossible through formal methods to do arbitrary code execution. And so essentially what they do is they have these rules. If you want to load a piece of code or JIT a piece of code into a tab, you have to pass all these rules. Before the code goes into there and starts executing, the verifier for the sandbox is going to make sure that all these rules are satisfied. And if these rules are satisfied, then it's basically impossible to the extent that we know how to break out. There's been a few interesting examples, but it's super tough to break through these defenses. So basically, once the binary is loaded, it's no longer writable. You can't create any new code inside this execution box once it's loaded and verified. It's statically linked, starts at 0, so there's no dynamic code flowing into this box. Indirect control transfers, indirect jumps, returns, calls to functions have to be done with this code sequence, which you'll notice jumps to a 32-byte boundary. Okay, so the entry points are every 32 bytes and only through EAX register. And so what happens is if you scan the code and you see that's enforced, no one's trying to jump without first doing this ANDing operation. Then what you do is you then go to all the 32 bytes and you analyze what kind of code could run at these 32 bytes. And you essentially do what's called a reachability analysis, and you can determine what is all the nefarious indirect jumps that could occur here. Can any of these indirect jumps do a system call that I'm not aware about or break any of these other rules? And if the answer is no, and you can actually complete that analysis, if the answer is no, then you can just say, okay, do whatever you want in this box. You're not going to be able to do something I'm worried about. So the binary is padded. If you go off the end of the binary before you get to the end of the page, boom, you hit a halt. So you're sort of limited to being inside that page. There's no instructions that overlap that 32-byte boundary, so you can't jump into the middle of an instruction. All valid instructions are reachable by a fall through. So it's a really fantastic piece of work. It's a software defense. It's a software defense that uses a software verifier so that once code goes into the box, it's safe. Now, how do you break this? There's a great attack using rowhammer, where Google rowhammered their code. After it passed the verifier for the native client, they went and rowhammered their own code, and that violated the C1 provision here. They were able to flip bits, and they knew which bits were likely to flip, and they flipped them in a way that allowed to break these other rules here, in particular the indirect jump rule. So such a clever attack, but generally very hard to do naughty stuff inside of a native client shell. All right, let's look at another hardware defense mechanism called a trusted platform module, or TPM. You may have heard about these before. TPMs are basically a security-focused second processor in the system that has a number of really unique features. It's really hardened. It's not generally programmable. It's really focused on security. It should reach a higher level of security standards than the remainder of the system. And it provides a bunch of functionality that you need to get the system into a known secure state. In particular, it helps us implement what's called secure boot. Can we use this unit here to limit what code can be loaded into the system? It's got a couple of really interesting features. For one, it has what's called an endorsement key, which is typically the public key of a third party, which we care about. So, for example, in the iPhone world, the public key of Apple, which is used, their private key is used to sign all the binaries that are allowed to go into the Apple execution environment. That would be an immutable memory inside the system somewhere in its TPM or TPM equivalent. And then another feature of TPM that's really popular, and you definitely want to see this on any TPM that you're going to work with, is the idea of signed storage, the ability to write into a store, typically non-volatile, but the only entity that can write into that storage is writes that have been signed with the associated private key of this public key that's burned into the TPM. And so now you have the ability to modify this storage only if you're the holder of the private key. If you're the vendor who controls this, that only you can write into that storage, modulo any security vulnerabilities in the TPM. And so, of course, we're going to need, hashing mechanisms. We're going to need some asymmetric key cryptography mechanism. And we're definitely going to need random number generators that we're going to provide that service to the system, et cetera. But we can use this thing to implement a lot of basic functions like trusted boot. So what is trusted boot? Trusted boot is a way to make sure that everything that's coming into my system is as I expect it to be. So the way I do that is I have every piece of code that's coming into my system, I have it hashed, and I have those hashes signed by this third party, whoever's associated with the endorsement key. And so I know if it's sitting in this non-volatile storage, they've been signed by that third party. So I look in this non-volatile storage, and then, before I start running the BIOS, the firmware in the system, the TPM will hash that storage and check to see if it matches its signed hash. And if it does, okay, no one's manipulated the BIOS. And then the BIOS will run. It'll initialize the initial system. We know the code's the code we expected. And then it'll load the bootloader, for example. And then the bootloader can be signed, and we can check those signatures with the TPM. And if nobody's modified the bootloader, then we'll let that run. And the bootloader will load the operating system, and then that'll be signed. And then the operating system will, and then eventually we get to the point where we're actually running the system, and then it can probe itself the endorsement key from the TPM, and it can check signatures. We don't need the TPM to do all this checking. And then you're booting with the known kernel, and now, and then I can continue this to the applications. I can say, hey, these applications have to be endorsed by this entity as well. That would be typical for like the iPhone environment. You're not able to run a binary on that system unless it's been signed by Apple, for instance. And this is very powerful, and it lets me get my system into a known state. Does it stop hacking? No, it doesn't. It just says that I know that the hacking that is occurring is not somebody replaced my operating system, right? Incidentally, that's what jailbreaking is. Jailbreaking is replace the operating system with something that's less restrictive than what the vendor wanted to create. And the way I jailbreak is I come up through this trusted boot sequence, I load the kernel, then I attack the kernel. I find a bug in the kernel that allows me to disable these checks on a reboot or replaces the kernel itself. So it's a fairly drawn out process. I need to, I essentially need to find a bug in the kernel to subvert the defenses that secure boot would have. This is it's a really good idea to have secure boot, because you can, you can get rid of rootkits and other things that where people try to change the installation of the system to try and be a part of your daily operations when you really don't want them. And Google's really been contributing to this effort through their OpenTitan project. OpenTitan is it's an open source TPM based on RISC-V infrastructure and a lot of open source crypto hardware and such. And it has built in a lot of defenses. It's looking to see if people are over temping or undervolting this chip. So I would say it's, as TPMs go, a very nice implementation that's got a lot of focus by the security community and use by Google and many other companies as well. This is really an industry-wide project. And so if you're looking for a TPM, definitely take a look at OpenTitan as a possibility. Now, are TPMs, are they the solution to strong security? No, right? Once we do secure boot, we can just attack all the software that's in the system. We can also attack the TPMs. Look, this is a RISC-V core here. It's running a CPU with software, and it's got lots of ports. Now, supposedly, we hope that the level of security and the level of inspection and analysis of the code running inside this TPM box is higher than the general system. So as a root of trust, should be pretty good. But, you can go to Black Hat, see examples of TPM attacks every year. So it's not a panacea, but it certainly makes a system more robust against attacks. And it is the root of trust that we'll use to implement our trusted boot. Trusted execution environments, or TEEs as they're called. These are from, ARM has the Trustzone TEE, Intel has the SGX TEE, AMD has the SEV TEE. These are really interesting capabilities, which essentially limit the amount of trust a process has to have with the rest of the system. Okay, so the goal is protect a process from all of the other processes in the system and the operating system. So I'm being distrustful of the operators of the system. I'm being distrustful of the underlying operating system. It's like, stay out of my stuff. I don't want anybody to know what I'm doing. So how would you use something like this? Intel's done a lot of work in the federated learning space, where they want to build these very large medical diagnosis models. And so they're moving these models from hospital to hospital, and they're running their code in Intel SGX in a way where they don't really trust the environment, right? This is my model. You're going to help me train my model. I don't want you looking at my model. I don't want you looking at my code. Just give me your data, your diagnosis data, your patient data, and I'm going to update my models. And so it's interesting where this environment has a number of very powerful capabilities. It lets you install a process where you can verify and authenticate with digital signatures that the code and the data, when the process starts, is as you expected. You get that assurance. And nobody can look into that process, presumably, because when anything comes out of that process into the memory system or the swap, it's encrypted with a strong cipher. So it's confidential. It's also integrity checked if you want to turn that capability on. And what that means is that if someone manipulates a value, like writes an old value there or just starts flipping bits on it, that'll be detected as well. So it has lots of strong, it's got the C and the I of CIA covered for many of these applications. So a really powerful capability. And being the operating system, being a super user doesn't get you into these directly into these. You can't look inside these boxes. And so what's interesting is it's really more than a security technology. It's really a basis to form privacy technologies, because now a third party can bring their data into your environment, and we don't really have to trust you and your operating system and your IT operators. That's very powerful and very exciting. Now, of course, there's challenges with any emerging security technology. And I think the challenges here are many. One is you're still making calls into code in the enclave, and people have demonstrated many times that you can just hack the code in the enclave. Now, the idea is the amount of code in the enclave is small. It's a small root of trust in the enclave. The rest of the system, the rest of the code of the system is outside in the untrusted world. So you are reducing that attack surface. There's less interfaces, less code to attack, but still very attackable. And you can do buffer overflows and, you know, all the standard stuff inside the enclave. Now, the enclave is a little restrictive in that you can only come in through the standard interfaces. But once you get into the standard interface, you can give it bad data and have it, you know, do all kinds of nefarious stuff. Another problem is the code that runs in the trusted execution environment typically runs on the same microarchitecture as the untrusted code. And so there's been lots of examples of microarchitecture attacks, including Spectre, Meltdown, Prime plus Probe, lots of ways to leak information out of these trusted execution environments. And for performance reasons, they tend not to encrypt memory above the DRAMs. The caches are decrypted. So, you know, it really leaves loads and loads of opportunity to leak information out of these through microarchitecture attacks. You know, to the point where I think you saw, you know, 3-4 years ago, a lot of talk about, you know, stopping disclosures and data leakage from TEs. I think most vendors today won't even mention whether or not these things can stop data leakage, because I think pretty much everyone agrees they're pretty leaky, these TEs. But in terms of protecting you for the operating system, I think they do a pretty good job. The leakage is both in terms of timing, transient fault attacks. The AMD trusted execution environments, their SCV environment, has even been shown to leak information through its ciphertext. So they have, in the way they present their ciphertext, it's often you can see in what the ciphertext is what the information is. Their ciphertext is not what's called semantically secure. It's not pure random data. It's correlated with what the encrypted plain text was. And so people have used that to do various hacks on AMD. So pretty much all these environments are getting hacked, but they do present a pretty strong capability. To give you a sense of how a program works, let's just kind of take a look at Intel SGX. The idea is you're going to have a big application running, but one part of the application is going to be the trusted part. You know, it's going to be the part that has access to, you know, the machine model that you're training, and the rest of it is just sort of shoving the local data up into it. And so the operating system can't really get into that box very effectively. It's got to side channel its way in or find a bug in the system. And so you're making calls through these call gates to these sort of trusted entry points in the SGX enclave, and then processing the data inside there. You really essentially, other than finding a vulnerability, you can't really see what's happening inside that box. And so from the standpoint of the programmers, it's just like, this part of my program, these functions are trusted and these functions are not. And then SGX's SDKs are going to orchestrate all that data movement into there. I think it's a really fantastic capability that really advances security to the point where, you know, we're starting to get into the zone of providing really a privacy technology here. You know, I can't know what's happening in that box other than the occasional vulnerabilities that occur. And then just, you know, at the tail end here, I want to talk about a related issue. People may not think of this as directly a security issue, but it is so fundamental to security that we need to talk about it at length, and that is random number generation. What are random numbers? In the world of security, random numbers are the keys that we're selecting for our protocols. If you remember to the TLS protocol that we looked at in the third unit of this lecture series, you know, one of the things that the client has to do is has to come up with a symmetric key. Key has to generate one and then send it to the entity that it wants to communicate with as it's encrypted with the public key of that entity. Well, generating that random key is, we want a true random number source. What does it mean to be a true random number source? That means that there's essentially no correlation to the creation of that value and the conditions of the system. I can't know what the conditions of the system are and recreate that random value. Now you can look back at, many disasters in the world of random number generation. You can find situations where the conditions of the system do give you information about the random number that was generated. A great example is like in early versions of the Netscape browser. If you're old like me, you probably remember Netscape was the predecessor to the Mozilla browser. The way they generated random numbers is they did a pseudo-random hash of the time of day the process started, the process ID, and the parent process ID. And so if you knew roughly when that process started, which you could look, you could see how long a process has been running. You can sort of reverse engineer values that were close to that. And then once you could guess that random number, then, now all of a sudden you can decrypt the encrypted communications going over the SSL link because you know what key they passed over to the other side. You don't have to break the crypto. You just figured out what the number is they passed. So that's what we want, is to generate random numbers that have no correlation to any aspect of the system. And that means we need to find what is essentially chaos. Remember back to Jurassic Park, where the scientist is always talking about chaos. That's what we need to make our random number generations. So where can we find this? One where you can find this is in human behavior. This doesn't happen today because there's so many TRNG sources, but back in the day when you would generate a PGP key, they would have you just kind of pound on the keyboard for a little while, and they would use the distance between those presses to generate sort of chaotic random information. Today, the way we generate random numbers is we look for subatomic phenomena like quantum noise, and we use that, which is pure random in nature, to generate our random numbers. So let's take a look. This is it's a little old, but this is was a chipset level random number generator that Intel disclosed a few years back. And basically what they did is they made an amplifier that could measure thermal noise, which is a sort of quantum effect on a diode where there's a little bit of leakage that goes through it, and the rate of that leakage is based on like the motion of the atoms at the junction, stuff that's like physics, right? And so what they notice is that process is very chaotic, and so then you take this reverse junction noise and you put it into an amplifier and you give it a little bit more power, but it's still pretty random. And then you use it to power a counter. So now the counter is going slow, fast, slow, slow, fast, fast, slow. So the rate of counting is the rate that's driven by this sort of thermal noise. Then you've got another counter, which is kind of, going at a fixed rate. And it's just sampling those counter values. And it's pulling a bit or two out of that, and it's shoving it into this latch, into this sequence of bits. And then you have this thing called a digital correlator, which tries to sort of throw away some of that information to make, over a short period of time, number of ones and zeros roughly balanced. It can do that in a way where it doesn't change the randomness, but we don't want like long sequences of zeros and ones. You probably don't need to do that, but they do this. And then you get that shoved into a FIFO, and then that's on the bus. And then your /dev random in Linux is going to allow you to pull stuff out of that. Now, the rate of production of information here is not, hundreds of terabytes per second. It's probably megabytes per second. So there is a limited rate at which this system can generate that thermal noise oscillation, the sampling of the oscillation, the correlators, and then filling this FIFO. But, you're getting megabytes per second. So what if you need gigabytes per second of random numbers? You're like, I don't know, salting encrypted packets for a high bandwidth gigabit Ethernet. So what you're going to do is you're going to set up a random number generator, like a Mercine's Prime, Mercine's Twister, for example. And then every time there's something in the FIFO, you're going to pull that out and you're going to reseed your pseudo random number generator. And then the pseudo random number generator is going to spit out numbers at whatever rate you want. LFSR, Mercine's twister, there's tons of algorithms that can do this, where given a seed, a starting value, produce random, pseudo-random values based on that number. And then when you get another little bit of information in that FIDO, you're going to stuff that into your pseudo-random number generator. So you can generate information at a high rate. It's just the rate at which the true random is coming into the system is really determined by your TRNG. I like to show this because I think it's really kind of a cool piece of work. This was done by one of my colleagues here at Michigan, David Blau, and it's a metastable based true random number generator. And I like to call this a piece of work that makes lemonade out of lemons, because what is metastability is this system, is this process where circuits essentially get wedged halfway between 1 and 0 because they tried to sample a value as it was going from 1 to 0. They sampled it right in the middle. And what happens in these circuits is, you kind of get ones and zeros chasing each other, and it's a real mess. The way this work came about is I was working with Professor Blau on some earlier work I did called Razor, which would lower the energy of a system, and then it would sample. It basically would take the outputs of stages until the stages started to fail. When they started to fail, often these circuits would go metastable. And so what David did is he basically built these metastable circuits, and he uses these very interesting controls to basically try to compensate for process variation and variation in the voltages to get them into states where they go metastable for a long, long time. And so what happens, you see these ones and zeros chasing each other in these circuits. That means they're basically in a metastable state. And the longer time that it takes to resolve that metastability, the more likely that the resolution of that metastability was due to something like quantum noise. There was just a little bit of a fine noise in the system that pushed it in one direction. They always do resolve, but the longer they resolve, often they take longer. So then what you do is you lay down, millions of these circuits are really tiny, and then you run them and you try to put them into these metastable conditions. And the longer that it takes to resolve, really the higher the quality of the true random bit is. And then so you basically have binned RNG, where you're producing these really high quality random numbers at a lower rate because it's rare that you get those long. And then you got these junky random numbers at the bottom, which are sort of random, but they resolve pretty quickly. And so you essentially create these qualified random numbers. Really fantastic. So true random, pure CMOS digital logic, and really easy to scale these to high bandwidth. Really cool information. And this is my most favorite RNG generator. This was the SGI LavaRand. I think Rackspace still runs these in their offices as well. And the basic idea is to just image a lava lamp. So what is a lava lamp? This is where you have like wax and water, and then there's a lamp. There's actually a light in the bottom of it, and it kind of shines up, and it lights the room. And what happens is the wax is melting, and it doesn't mix with the water, and so you get what's called a turbulence effect. And turbulence is a chaotic effect in nature. And so how these shapes form in the lava lamp is the result of true chaos from nature. It is true random information. And so the way you digitize that information, you just take an image of the lava lamp and then you hash the image, and then that is a true random number. Really interesting. So I think it's Rackspace, but they have in their entry of one of their offices, they have a whole they have an entire wall of these lava lamps, and then there's a camera that takes a picture of the office, and that generates random numbers. Such a clever idea. There's a patent that described this as well. Let's just hit a few discussion points before we end this unit. Should we avoid ever again using C and C++? I think if you can avoid using C and C++, why not, right? You're going to significantly reduce the attack surface of your software if you can avoid using C and C++. You have to have the performance headroom necessary to use those less efficient managed languages. But you're also going to have productivity too. It's so much easier to program in, a big system in Rust or Python than it is to write it, especially in C. So, but of course we can't get rid of C and C++. We're going to write our operating systems typically in that. We're going to write our video games that are performance centric in that. We're going to write our runtimes. So we're still going to see, it's going to be a long time before we see the end of C and C++. Is it ever wise to utilize XOR as an encryption cipher? I would say definitely not. There's a couple of reasons why, right? Any disclosure reveals the key, right? Because the key XORed with a thing is the encrypted thing. Well, the encrypted thing XORed with the knowledge of what that thing should be is the key, right? That's the associative property of XOR. That's a problem. The second problem is there are homomorphisms on XOR that are really dangerous. Let me give you an example of one. Let's say you XOR encrypt your binary and you don't know what the key is, but you know which one of the instructions is a branch less than or equal. You can flip a bit of the ciphertext and you will flip a bit in the instruction and you can make it a branch greater than, the opposite. Pretty easy to do those kind of attacks. So XOR is weak encryption, and weak encryption can be easily broken. You take asymmetric key cryptography like Karma from Qualcomm, or AES, which is the US standard, or Simon, which is a hardware-based cipher I really like. In those cases, basically, if you flip any bit, you've destroyed the information, right? And there are no homomorphisms that we're aware of for those. Can TEE side channels be fully addressed? That's a great question. I would say as long as they're sharing the microarchitecture with the untrusted protection domains, including the operating system, I would say no, because there's just, just go back to the last lecture, the side channel lecture. There's just too many mouse tracks we can put between these two things. There's too many ways to communicate. There's too much microarchitectural state. I don't see a possibility of doing that. The idea I like to explore in my research is the idea of TEEs that are their own silicon, right? And then we build strong proofs, formal verifications over the timing, memory, control characteristics of those TEEs. I think that's a much more interesting, certainly much more expensive approach, but I think if you're really serious about getting rid of side channels in trusted execution environments, there has to be a divorce in our future between the microarchitecture and the TEE. Okay, and then the last question. I'm using a deterministic circuit program framework. How can I generate true random numbers? This is a really interesting question. I've run into this problem myself. If you use FPGAs in the cloud, they do not allow any non-deterministic execution of logic in the cloud. But there's a great researcher at Yale, Yakub Zephyr, who has published many, many ways to break those rules. What he does, he just breaks the rules. He figures out ways to make asynchronous logic that they cannot detect with their analysis tools. But let's say you're not as clever as Yakub, and you can't figure out how to make asynchronous logic that they cannot detect. Then I think you need to find other sources of randomness in the system. And I would say a great source of true random events are interrupts, right? Because interrupts come from other clock domains, and bus events, especially on a chip multiprocessor, where each of the individual processors are under its own clock domain. In this particular case, it's very much the case that you should be able to find true random chaos in the arrival time of those events. All right, that is existing hardware and software defenses, and looking both at their capabilities, the threats they stop, and maybe some of the restrictions as well. Thank you for watching this video. In the next and final installment of this 6-part video tutorial series on hardware security, we'll look at emerging technologies, both my research and other people's research. And one of the things we'll see in the emerging technologies in particular is this movement away from trying to find, detect, and stop vulnerabilities, instead moving, leaning, many of these technologies leaning really heavily into crypto. I said in the second unit here that the only superpower in the world of security is cryptography. And the more you snuggle up with cryptography, the better the outcomes of your defenses are going to be. So you can see in this next unit 6 with emerging technologies, lots and lots of crypto. So thank you for watching this video. If you have any questions, please don't hesitate to reach out to me. I'd love to interact. I love to interact with my YouTube viewers. Please like this video, subscribe this channel if you find this interesting. I have a pretty steady rate of pretty technical content coming out on my channel, and I would love to have you see that and interact with me again in the future. Thank you so much for watching this video, and take care.